Have you ever looked at the periodic table and wondered why it's shaped like a staircase of blocks? Why do some rows have just two elements, while others stretch across almost the entire table? Well, these rows are called periods, and they hold the key to understanding atomic structure. A period is a horizontal row of elements arranged in increasing order of atomic numbers. There are 7 periods in the modern periodic table. Each period starts with an element that begins a new electron shell. That's right, the period number actually tells you how many electron shells or energy levels an atom has. For example, hydrogen and helium are in period 1, meaning they have only one shell, the K shell. But sodium and chlorine, found in period 3, have three shells, K, L, and M. Not all periods are created equal, some are short and sweet, others are long and complex. Period 1 is the shortest of them all, with just two elements, hydrogen and helium. That's because only two electrons can fit in the first shell. Then we have periods 2 and 3, each with 8 elements. This is where the L and M shells begin filling up. As we move to period 4 and beyond, things get more crowded. Period 4 has 18 elements, including the transition metals like iron, copper, and zinc. Now, here's where it gets really interesting. Periods 6 and 7 each have 32 elements. Why so many? Because we now include entire rows of lanthanides and actinides. These are the rare earth and radioactive elements, respectively. So, yes, that separate strip of elements below the table, they're actually part of the main story. Let's zoom into period 2, one of the most fascinating rows in the periodic table. It begins with lithium, atomic number 3, and ends with neon, atomic number 10. All these elements have two electron shells, that is, the K shell is filled and the L shell is being filled across this period. As we move from left to right, we see a transformation in chemical character from lithium and beryllium, which are metals, to boron, a metalloid, and then carbon, nitrogen, oxygen, and finally fluorine and neon, which are nonmetals. The valency also changes, starting from 1 for lithium, increasing to 4 for carbon, and then reducing back to 0 for neon, which has a complete octet. Let's now explore period 3 from sodium, atomic number 11, to argon, atomic number 18. All these elements have three electron shells, K, L, and M. As we move across this period, the outermost shell, the M shell, is being filled one electron at a time. The progression goes like this: sodium to 8, 1 magnesium to 8, 2 aluminum to 8, 3, and so on until argon to 8, 8. Just like in period 2, period 3 also starts with reactive metals like sodium and magnesium, transitions through metalloids like silicon, and ends with nonmetals like chlorine and the noble gas argon. Again, we see valency rise from 1 to 4, then fall back to 0, forming a perfect wave of chemical reactivity. What really makes periods powerful is the trend in properties you can observe across a row. First, all elements in the same period have the same number of electron shells, only the number of protons and electrons increase. Now, with every step to the right, the valence electron count increases by 1. This leads to several changes. Atomic radius decreases because more protons pull electrons closer. Ionization energy increases, making it harder to remove an electron. Metallic character decreases and nonmetallic character increases. Take period 2. Lithium is highly metallic, while fluorine is a strong nonmetal. That's a complete transformation across a single row. This trend helps chemists predict how elements behave even if they've never handled them in a lab. As we move from left to right in a period, the nature of compounds formed by elements also changes dramatically. Let's talk about oxides, compounds formed with oxygen. Sodium oxide, Na2O, is strongly basic magnesium oxide. MgO is basic aluminium oxide. Al2O3 is amphoteric silicon dioxide. SiO2 is weakly acidic. Phosphorus pentoxide, P2O5, is acidic sulfur dioxide. SO2 is strongly acidic. Chlorine heptoxide, Kl2O7, is very acidic. You can see the acid-base character shifts from strongly basic to strongly acidic across a period. This is mirrored in their hydroxides as well, from strong bases like NaOH to weak acids like H3PO4 and strong acids like HClO4. Even bonding types shift. Sodium chloride is ionic, while silicon tetrachloride is covalent. These progressive shifts show how beautifully chemistry follows patterns in the periodic table. Let's quickly wrap up what we've discovered about periods in the periodic table. We learned that each period represents a new shell being added to atoms. As we move across a period, atomic number increases. Valency follows a wave-like pattern. Electronegativity increases, bonding type shifts from ionic to covalent. Acid-base character transforms from basic to acidic, metallic character decreases. We also touched on bridge elements like beryllium and boron, which behave like a mix of their own group and the next one. So, the next time you look at a row in the periodic table, remember, it's not just a line of symbols, it's a journey through atomic architecture, bonding behavior, and chemical reactivity. I hope this session helped you see how periods shape the logic of chemistry. In the next class, we'll explore the groups and their significance. Get ready to meet the families of the periodic table. See you there.